Pa-record, okay. Pa-record na lang Iniga. Okay. So, sa group ng sunod po mag-represent, composite. So, ready na po ba kayo?
Ready na po, ma'am. I-present ko na lang po.
Okay po. So, thank you po. You may proceed po with your presentation.
Hello po, good morning everyone. Today po, we are going to discuss about composite materials. But before we delve into the details of it, let's start first our discussion with an overview of composite materials. Next slide po. In this presentation, we will be focusing on the four main divisions of composite materials and the distinguishing features of each, the differences between large particle and dispersion-strengthened particle reinforced composites, the three different types of fiber reinforced composites on the basis of fiber length and orientation, the three common fiber reinforcement used in polymer matrix composites and its desirable characteristics and limitations, the desirable features of metal matrix composites, and finally, the two sub-classification of structural composites.
Roy.
Now that we have a brief overview, let's define what a composite material actually is. Next slide po. From the word itself po, a composite po is any multi-phase material that effectively combines properties from its different phases, creating a more advantageous set of properties than each component alone. In other words po, composite materials po are made when two or more materials or phases are combined together to get unique set of properties which cannot be achieved otherwise by the individual material or phase. So when we see po one material with a certain property and another material with different property po, it's often difficult po to find a single material that combine both of these properties. So therefore po, we combine these two materials or phases to create a composite with a unique set of properties that wouldn't be achievable with any single material alone. Furthermore po, most composites po have been created to improve combinations of mechanical characteristics such as stiffness, toughness, and ambient and high temperature strength. Next slide po. There are mainly two phases in composite materials. One is matrix phase and the other one is disperse phase. Matrix phase po is a continuous phase which is surrounding the disperse phase. So ano po, I have a sample representation of composites here. So as you can see po in the picture, the dispersed phase po or yung yellow or yung orange po na color is surrounded by the continuous phase known as the matrix. To continue po the discussion about composite materials, I would like to introduce Mr. Abelros po.
Before po tayo mag-proceed, pwede panoorin po muna natin po yung video tungkol po sa what is composite po to further understand po the topic po.
What is a composite? To understand what this material is composed of, let's take a closer look at its structure. It has at least two different components whose properties complement each other. The first is most often made up of technical fibers, such as glass or carbon fibers, and is used to reinforce the strength of the product. This is referred to as reinforcement or fiber reinforcement. The second component is a binder. It can be a plastic or polymer resin. This matrix ensures the cohesion of the structure. The materials thus obtained have properties that the components on their own do not have. Take the example of this car. In 5 years, it will weigh 250 kilograms less and allow energy savings of 0.4 liters per 100 kilometers. Furthermore, composites on the whole have an advantage of being very resistant and are much lighter than metals. Arkema even recycles thermoplastic resin-based composites through its helium solution. Composites, due to their properties, can be used in varying ways, especially in ship's hulls, sports accessories for motorsports, car parts, or fuselage for the latest generation aircraft. Today is a major opportunity for our this field of innovation. In the
Now let's proceed to classification of composite materials. Classification of composite materials have four main division: vertical composite, fiber reinforced, structural, and nano. First is the particle reinforced composites. Contains dispersed particles with similar dimension in all directions, creating a corresponding structure. Fiber reinforced composites. On the other hand, it feature a dispersed space shaped like fibers with a high length to diameter ratio, which enhances their strength and flexibility. Structural composites are multi-layered, engineered to be lightweight with excellent structural integrity, which makes them ideal for load-bearing applications. Last is nanocomposites. Involve particles in the dispersed space that are measured in nanometers, which bring unique properties like increased surface area and improved thermal or mechanical characteristics.
The first classification of composite materials is particle reinforced composites. Next slide. There are two subclassifications of particle reinforced composites. First is large particle composites. The term large is used to indicate that particle matrix interactions cannot be treated on the atomic or molecular level. Rather, continuum mechanics is used. For most of these composites, the particulate phase is harder and stiffer than the matrix. These reinforcing particles tend to restrain movements of the matrix phase in the vicinity of each particle. Next slide. There are three examples of large particle composites. First is polymers with filler. The fillers modify or improve the properties of the material and or replace some of the polymer volume with a less expensive material. Second is cermets. The most common cermet is the cemented carbide, which is composed of extremely hard particles of a refractory carbide ceramic, which such as tungsten carbide or titanium carbide, embedded in a matrix of a metal such as cobalt or nickel. These composites are utilized extensively as cutting tools for hardened steels. And the last example is concrete. Concrete is a common large particle composite in which both matrix and dispersed phases are ceramic particle materials. Concrete implies a composite material consisting of an aggregate of particles that are bound together in a solid body by some type of binding medium that is a cement. Next slide. The two most familiar concrete are Portland cement concrete. It is employed extensively as a structural building material, and the second is asphaltic concrete. It is widely used primarily as a paving material. In the picture, you can see the example specimen of Portland cement concrete and asphaltic concrete. Next slide. The second subclassification of particle reinforced composite is dispersion strengthened composites. For dispersion strengthened composites, particles are normally much smaller with diameters between 0.01 and 0.1 meters or 10 and 10 nanometers. The dispersed phase may be metallic or non-metallic oxide materials are often used. The dispersion strengthening effect is not as pronounced as with precipitation hardening. However, the strengthening is retained at elevated temperatures and for extended time periods because the dispersed particles are chosen to be reactive with the matrix phase. Next slide.
And now for fiber reinforced composites. Pakinig po ba yung audio? As pa-heart naman po, okay lang po yung audio. Thank you. And now we're going to discuss about the fiber reinforced composites. First, let's know what is fiber reinforced composites. Fiber reinforced composites are composites type that are material where fibers embedded in another substance called the matrix. This combination of fiber matrix is designed to create a strong, lightweight material. And next po. And the goal of having a fiber reinforced composites is first is for the strength, stiffness, the specific strength and modulus. Having reinforced by fiber, the normal material can be enforced. It can, kumbaga, mas mapapalakas, mas mapapatibay, at it can accumulate more force. Kasi nga, with respect sa force, yung stress na paglaki ng force is parang, limbawa, meron tayong area ng material or simple material, having force applied, it can reach its breaking limit or the critical stress. So having a fibers reinforced material or composite, mas mapatibay o mas mapapaganda, having the same amount or same size pero mas mapapatibay yung mga bagay-bagay or yung material na kailangan ng engineering, which is karaniwang ginagamit natin in our field or engineering field. Next po. And in fiber reinforced composites, it is divided into two, which is the continuous fibers and discontinuous fiber. Ang pinagkaiba lang po ng dalawa na ito is for continuous, it is composed of long material or long fibers, while the discontinuous is short fibers. In continuous fibers, ang purpose po ng having long is for it to transfer effectively yung stress, significantly reinforcing the material. Which, sabi ko nga kanina, or sa ating normal stress formula na stress is equal to force over area. Having a long side or long width, it can create a bigger area, which is directly proportional to stress. So having a bigger area, mas mapapaliit yung stress, which is mas mapapatibay yung bagay or mas marami siyang force na kayang i-accumulate. And for discontinuous fibers naman is having shorter than critical length. Kumbaga mas maliit siya compare sa continuous fibers. And which is in fiber reinforced material, mas maganda yung ginagamit na continuous fibers since in our field na, mas maganda yung mas malakas o mas maraming force na kayang i-attain ng isang material para mas maging matibay yung ating mga ine-invento or ating mga structures. Pero both of these have both uses in different or specific uses. Next po. And next is the arrangement of the fiber reinforced materials. First is the orientation. In orientation, we have two, which is the align and random. From the words, it indicates align. Ito yung iisa or parang nakahanay siya. And in random, it different order. In aligned fibers, it is oriented in single direction, as I said. This alignment often enhances properties like strength and stiffness in direction. Kumbaga, ang ine-enhance niya is properties ng strength and stiffness in a single direction. While in random, it is randomly oriented, which indicates more uniform properties in all directions. Since random nga siya, so in all directions yung parang orient niya. And next is the concentration and distribution. Having the amount and evenness of fiber distribution throughout the matrix also play a crucial role. Uniformly distributed fibers tend to yield better and more predictable composite properties. So in concentration and distribution, syempre as we know naman, pag marami yung fiber, alam naman natin yung fiber, no? Pag marami, mas matibay. Like, example of this is, pag uniformly distributed siya, example is this sa spaghetti. Spaghetti stick na yung hindi pa luto. So, pagdami nung spaghetti stick, mas matibay yung, o mas marami tayong ilalapag natin siya or papatungan natin ng bagay, mas marami or mas mabigat yung mailalagay natin compare sa kakaunti yung bilang. Next po. And ito po yung schematic diagram nung kanina. First is the letter A, yung continuous and aligned. Sabi ko nga, in single direction, tas mahahaba. Tapos sa B naman, makikita natin dito yung discontinuous and aligned. Maliliit siya, pero naka-align pa rin. And next one is the letter C, which is yung fiber reinforcing randomly. Yan yung pagkakaiba nung tatlo in combination. Nung dalawa with combination ng orientation. Next po. And these are the examples of fiber reinforced materials. The whiskers, which contains graphite, silicon nitride, aluminum oxide, silicon carbide. Next po. Next is the fibers. Yung fibers na kilala natin. Aluminum oxide, aramid, carbon, e-glass, boron, silicon carbide. Next po. And lastly is the metallic wires. Yan po yung high-strength steel, molybdenum, tungsten. And for us discuss that, next slide po, ito po yung specific details nila. Yun nga po, fiber phase. An important characteristic of most materials, especially brittle ones, is a small diameter fiber is much stronger than bulk material. On basis, diameter and character fibers are grouped into 3 different classification. The whiskers, fibers, and wires. And now, let's discuss the whiskers. Next po. Ang whiskers, these are thin single crystals that have extremely large length to diameter ratios. They are among the strongest known material. Highlighted work is ang whisker daw ay kilala sa isa sa pinaka-strongest material na ginagamit sa engineering field. The whisker materials include graphite, silicon carbide, silicon nitride, and aluminum oxide. Ito po yung picture, hindi po masyado malinaw since fiber naman siya, maliliit po siya. Next po. And next is ang pinakakilala natin, which is the fibers. Materials that are classified as fibers are either polycrystalline or amorphous and have small diameters. Fibrous materials are generally either polymers or ceramics. Kumbaga yung mga fibers ay, ito yung makikita natin yung mga sa fiberglass, yung sa carbon na sasakyan, makikita natin yung mga fibers na ganun. And which is the polymer aramids, glass na yung sabi ko, carbon boron, aluminum oxide, and silicon carbide. Next po. And the last is the wires. Fine wires have relatively large diameters. Typical materials include steel, molybdenum, and tungsten. Wires are utilized as radial steel reinforcement in automobile tires, in filament rocket casing, and in wirewood and high-pressure hoses. Kumbaga, ang mga wires, it is a fiber reinforced materials. Pag sinabi natin fiber reinforced materials, combination siya ng maraming materials na kung saan ay hibla siya para mas mapatibay yung mga specific or yung normal invented materials. Example ito ay yung sa gulong. Kung makikita natin po yung gulong, kung sino man po nakakita sa inyo na, pag biniyak po natin yung gulong, may makikita po tayong mga hibla-hibla dyan na parang bakal na wire. Yan po yung example ng wires. And also yung wires po ay example din yan ay sa different, halimbawa na lang po dyan sa ating wire ng mga Meralco, parang naka-fiber reinforced po siya. Yung pattern po niya, para mas matibay, para hindi agad maputol or hindi agad masira. And also, example din ito ay sa hoses. Kung dun sa ating plumak, may makikita tayong hoses na yung hindi transparent. Pag hinati natin yan, may makikita tayo sa gitna na mga fiber Yun yung example of fiber wires reinforced composites. Next po.
Sa ano naman po, sa polymer matrix composites or yung PMCS po is composed of polymer resin matrix with fiber reinforcement with such as po yung mga glass, carbon or aramid materials po that embedded within a polymer matrix. The polymer matrix binds and supports the fibers, allowing for an efficient load transfer and adding durability to the composite. And it is widely used po in various industries for their high strength to weight ratio, durability, and resistance to corrosion po. These composites are valuable in application requiring lightweight materials such as aerospace, automotive, sports equipment, and infrastructure. And ito po yung mga types po ng polymer matrix composites po. First is the glass fiber reinforced polymer or GFRP. These composites use glass fibers within a polymer matrix, providing strength, durability, and resistance to environmental factors. They are commonly used in automotive, marine, and construction application due to their cost effectiveness and versatility. Next is the carbon fiber reinforced polymer or CFRP composites made with carbon fibers, and CFRP composites are known for their high strength to weight ratio and stiffness. They are widely used in aerospace, automotive, and sport industries where lightweight and yet strong materials are essential. Next is the aramid fiber reinforced polymer composites. Utilizing aramid fibers like Kevlar, these composites are valued for their excellent impact, resistance, and toughness. They're often used in the ballistic protection and aerospace and military application. And the other fiber reinforced materials, this category includes fibers like basalt and natural fibers offering specific benefits like improved environmental sustainability, cost effectiveness, and unique mechanical properties suited for niche applications. And last is the polymer matrix materials. The matrix materials itself can vary, typically thermosetting or thermoplastic polymers. The matrix bind the fibers, transferring load and providing the composites overall shape, flexibility, and durability. And dito po sa picture na po, ito po yung mga example po ng glass fiber, yung carbon fiber o yung aramid fiber and mga basalt fiber, and last po is the polymer matrix.
Metal matrix composites. Metal matrix composites, composed of a ductile metal matrix. High temperature use can withstand higher surface temperatures than base metals. Enhanced properties, reinforcement improves, and specific stiffness and specific strength. Abrasion and creep resistance, thermal conductivity, and dimensional stability. Next slide, please. Some of the advantages of these materials over the polymer matrix composites include higher operating temperatures, non-flammability, and greater resistance to degradation by organic fluids. The reinforcement may be in the form of particulates, both continuous and discontinuous fibers and viscose. Continuous fiber materials include carbon, silicon carbide, boron, aluminum oxide, and the refractory metals. However, discontinuous reinforcements consist primarily of silicon carbide viscose, chopped fibers of aluminum oxide and carbon, or particulates of silicon carbide and aluminum oxide. Next slide, please. So these are the subtypes of a metal matrix composites. First one is the aluminum matrix composites. Composites with aluminum as the main matrix, offering enhanced strength, wear resistance, and sometimes good thermal conductivity. Magnesium matrix composites. Lightweight composites with magnesium as the matrix, providing a combination of low weight and improved mechanical properties. Next slide, please. Titanium matrix composites. Composites based on titanium, known for high strength, stiffness, and high temperature resistance. copper matrix composites. Composites with copper as the matrix, having properties like high thermal and electrical conductivity, along with enhanced mechanical characteristics. Next slide po. Ceramic matrix composites. Ceramic materials resist oxidation and deterioration at high temperatures. Brittle fractures limit their application's potential. Could be ideal for high temperature, high stress environments. Potential use in automobile and aircraft gas turbine engine components. One particularly interesting toughening technique uses a phase transformation to arrest the propagations of cracks and is aptly termed transformation toughening. Other recently developed toughening techniques involve the use of ceramic whiskers. Ceramic matrix composites may be fabricated using hot pressing, hot isostatic pressing, and liquid phase sintering techniques. Next slide po. So these are the subtypes of ceramic matrix composites. First one is the carbon fiber reinforced ceramic matrix composites. These composites consist of a carbon fiber reinforcement embedded in a silicon carbide matrix. They offer a high strength, stiffness, and thermal conductivity, making them suitable for applications in aerospace, defense, and high temperature industries. Next slide po. Silicon carbide fiber reinforced ceramic matrix composites. These composites are composed of silicon carbide fibers embedded in a silicon carbide matrix. They have excellent high temperature strength, oxidation resistance, and creep resistance, making them ideal for use in gas turbine engines, nuclear reactors, and other high temperatures applications. Next slide. The last one is the alumina fiber reinforced ceramic matrix composites. These composites consist of alumina fibers embedded in alumina matrix. They offer high strength, hardness, and wear resistance, making them suitable for applications in cutting tools, wear parts, and biomedical implants. Next slide. The glass ceramic matrix composites. Glass ceramic matrix composites are composed of glass ceramic matrix reinforced with ceramic fibers or particles. They offer good mechanical properties, thermal stability, and chemical resistance, making them suitable for applications in aerospace, electronics, and even in biomedical industries. Next slide. The oxide ceramic matrix composites. These composites consist of an oxide matrix reinforced with oxide fibers or particles. They offer high strength, toughness, and oxidation resistance, making them suitable for applications in aerospace, defense, and even in energy industries. Next slide po. The carbon-carbon composites. Carbon-carbon composites composed of carbon fiber reinforcements and carbon matrix, advanced engineering material with high potential, new and expensive, limiting extensive use, and not widely adopted due to high cost. Uh, the carbon-carbon composites are employed in rocket motors as friction materials in aircraft and high-performance automobiles, for hot pressing molds, in components for advanced turbine engines, and as ablative shields for entry vehicles. Next slide po. The hybrid composites. A relatively new fiber reinforced composite is the hybrid, which is obtained by using two or more different kinds of fibers in single matrix. Hybrids have a better all-around combination of properties than composites containing only a single fiber type. A variety of fiber combinations and matrix materials are used, but in the most common system, both carbon and glass fibers are incorporated into polyramic resin. So the glass carbon hybrid is stronger and tougher, has a higher impact resistance, and may be produced at a lower cost than either of the comparable all carbon or all glass reinforced plastic. Principal application for hybrid composites are lightweight land, water and air, transport, structural components, sporting goods, and even lightweight orthopedic components. Next slide, please.
And now for the processing of fiber-reinforced composites. Ito yung kung paano ba ginagawa or ano ba yung mga methods on how to make a fiber-reinforced composites. The processing of fiber-reinforced composites are to create continuous fiber-reinforced plastics that meet specific design requirements. The fibers should be evenly spread out within the plastic matrix in the most cases. Align in same direction. And here are the three main fabrication methods. Next po. First one is the pultrusion method. This technique is used to produce the parts to have continuous lengths and constant cross-section, such as rod, tubes, and beams. During pultrusion, fibers are pulled through a resin bath to coat them. The plastic then shaped and cured to form long continuous profiles. And here is the schematic diagram of pultrusion process. And for us to further para mas maintindihan natin, may video po kami para dyan. Next po.
Pultrusion process. Pultrusion is a process for the continuous production of composite profiles with constant cross-sections and material properties manufactured for specific purposes. The method ensures a consistent quality that can be reproduced time after time. Learn more about the steps from raw materials to finished products in this video. Unidirectional continuous fibers, like glass and carbon, are being pulled from the creel stand. Depending on the product type, woven fabrics, mats and surface veils are pulled from the shelves. The reinforcement package is pulled through a guide where the fibers and woven fabrics are placed precisely in relation to the profile cross-section. When the reinforcement is pulled into the die, the matrix is added by injection. The matrix includes thermosetting polymer resins as well as process and product-related additives. The injection method is a fully enclosed process that keeps evaporation of solvents at a minimum. This ensures a good work environment in comparison with traditional pultrusion, where reinforcement is led through an open bath containing the matrix. After the fibers are impregnated with the injected matrix, the entire product moves forward to the next zone in the process, where heating takes place and where the curing of the profile is accelerated. The pulling power needed to overcome friction in the processing equipment, and thus the driving force in the process, is provided by pullers placed outside the processing equipment. Pulling can be done by either belts or reciprocal pullers. Depending on the cross-sectional area of the produced profile, pulling force of up to 50 tons are possible. During the last phase of the process, the profiles are shortened by a saw mounted to move at the same speed as the profile being pulled out of the die. This ensures a continual process with no stops, even when cutting. Fiberline's composite profiles combine a number of unique advantages that are not found together in other traditional materials. This makes our profiles a cost-effective option for the sustainable construction of the future, where we can create more with less. Get an overview of all the advantages in our animation videos. Fiberline. Create more with less.
So, yun po yung pultrusion method. And next one is the prep-red production process. In this method, continuous fiber are pre-coated with partially cured polymer resin, creating a material called prep-red. Prep-red is typically supplied as a tape, allowing a manufacturers to directly mold and fully cure the composite without needing additional resin. This process ensures consistency in resin distribution and fiber alignment. And here the schematic diagram of the prep-red. And halos same lang din siya po dun sa pultrusion na gumagamit siya ng resin. Pero mas kakaunti po yung resin na nagagamit dito sa prep-red production process. And for us to know kung ano po ang prep-red production process, may video review kami dyan. And next is the filament winding. This process is used to create a hollow paper shapes, usually cylindrical, like in pipes or tanks. In filament winding, continuous fiber are wound in specific patterns around a rotating mandrel, forming a precise fiber layout. After winding, the structure is cured to harden the resin and lock in the fiber configuration. Kumbaga ito yung parang mga wires like in motors, pero ito naman yun ang ginagamit sa materials like sa gulong, sa ganun, para mas mapatibay yung foundation ng isang structures. And for us to know kung ano man yan, kung ano ang filament winding, may video rin po kami.
One of the processes used to make tubular products is filament winding. A filament is a fine strand of a material that looks like a thin wire. Filament winding involves pulling glass or polymer fiber strands through a resin tank, then winding the resin-covered fiber reinforcement onto a rotating shaft called a mandrel. As the resin gels and cures, it bonds the fiber filament windings and forms a rigid tube of fiber-reinforced polymer composite on the mandrel. When the resin is fully cured, the mandrel is removed, leaving a polymer composite tube. The filament windings can be clearly seen on this carbon fiber fishing rod. Filaments can be wound onto the mandrel at right angles to it, and filaments can be wound diagonally. Multiple layers may be laid in opposite directions so that each layer reinforces the one next to it. Tubes made by filament winding are used to make paddles and oars, windsurfer masts, dinghy and yacht masts, fishing rods, golf club shafts, spade, shovel and garden rake handles, and other tubular and cylindrical products. Examples of fibres used in filament winding are glass fibre, carbon fibre and aramid fibre, that is Kevlar, and examples of resins used in filament winding are vinyl ester resin, epoxy resin, polyester resin and phenolic resin. Finally, I'd like to thank you for watching and I hope that you found this video helpful.
And with that, those are the three processes. And for the next one is the structural composites.
Hello po, rinig po ba ako? Ayun, let's start po sa structural composite. What are structural composites? Next po. These advanced materials are made from two or more different materials, normally composed of both a homogeneous and composite materials that are combined to achieve enhanced properties. They are designed in mind to provide utmost strength and stability while keeping the material itself lightweight, making them an ideal material for various applications, especially in the world of construction and aerospace. There are two types of structural composites, which are the laminar composite and sandwich panels. Next po. Laminar composites are made from sheets or panels bonded together where each layer is oriented for maximum strength. Common configurations include unidirectional, where all of its fiber are facing in one direction. While in cross-ply fiber, its fiber are stuck together at a 90 and 0 degree angle. And angle ply is kind of the same with cross-ply, but now its fiber is alternating at an angle. Like in the figure where it's in positive 40-degree angle and negative 45-degree angle. And for the last configuration is the multi-directional configuration, where it's or plywood, and their job is to carry the bending loads. And the sandwich material is called the core, which is made from a lightweight material and normally has a low modulus of elasticity. Next po. And the benefits of using these structural composites, first is it is lightweight and strong. These composites can be much lighter than the traditional material like metals while providing a comparable or even superior strength. Second, it has a customizable property. By altering the type of materials used in the arrangement, its properties can be tailored for a specific application. And lastly is its durability. Most composites have high resilience against fatigue and environmental damage, making them suitable for demanding conditions better than traditional materials. So to sum it all up, structural composites combine different materials to create strong, lightweight solution tailored for specific engineering challenges across various industries. Thank you po.
Yan, hello po, rinig po. Yan, bale, natapos na po natin kanina or na paliwanag po yung ating three main divisions po dun sa apat na classification of composite material. Ngayon, mag-proceed naman po tayo kay nanocomposite. Next slide po. Now, ano nga po ba si nanocomposites? A nanocomposite is a composite material or multi-phase solid material where one of the phases has 1, 2, or 3 dimensions of less than 100 nanometer or a structure having a nanoscale repeat distance between the different phases that make up the material. Next slide po. So mechanically po, the term ng nanocomposites po natin is differ from conventional composites due to the exceptionally high surface to volume ratio of the reinforcing and or its exceptionally high aspect ratio. Si nanocomposite matrix materials po natin is pwede po siyang maging pwedeng metals, pwedeng ceramics and polymers. Pero kalimitan po na ginagamit natin na nanocomposite matrix materials is yung ating polymers po. Next slide po. Ngayon, ano po ba yung general characteristic ni nanocomposite? It consists of one or more discontinuous phases distributed in one continuous space. Si continuous space po is tinatawag natin siyang matrix, while si discontinuous space naman po is called reinforcement or reinforcing material. And para po mas maintindihan natin ano po ba yung pinagkaiba ni matrix and reinforcing material, si matrix po is typically po is softer po siya and it holds po yung the reinforcing material natin together, which yung common matrices po natin includes po the polymers, the metals, and the ceramics. Ang primary role ni matrix po is to bind po yung ating reinforcements in place and distributing loads to them and providing the material with overall shape and cohesion. Add lang po natin kay matrix na it also protects po yung ating reinforcing material from environmental damage like yung corrosion po and wear. While si reinforcing material naman po are usually stronger and steeper than the matrix. It provides po the composite with enhanced mechanical properties such as higher strength, stiffness, and sometimes improved thermal resistance. Si reinforcements po or reinforcing material natin come in various forms like fibers. Ano po ba yung mga fibers na yan? Like glass, carbon, or aramid fibers, particles, and flake. And they carry most of the load when the composite material is under stress po and help prevent the matrix from deforming. Ngayon, ano po ba properties ni nanocomposite? Hindi lang po siya nakadepende dun sa properties ng both matrix and nanoparticle, but also on the nanoparticle shape and content as well as matrix po. Next slide po. Ngayon po, meron po tayong two classification of nanocomposite and nahati po siya sa dalawa, which is the polymer-based and the non-polymer-based. Si polymer-based nanocomposite po natin is composite use polymers as matrix material, the incorporation of nanoparticles like nanocarbons, nanoclays, or nanocrystals. While si non-polymer-based nanocomposite, in this composite, the matrix can be inorganic materials like metals, ceramics, or glass. So, ang pinagkaiba po ni polymer-based kay non-polymer-based, si polymer-based po, these are nanocomposites have a polymer matrix like epoxy, polyethylene, embedded with such as carbon nanotubes, yan nga po, nanoclays or metal oxide nanoparticles. Si polymer-based nanocomposites natin or yung polymer matrix natin is mas nakakapag-provide po siya ng mas flexible, mas madaling gamitin for processing and lightweight properties. While while the nanoparticles enhance po yung kanyang mechanical strength, the thermal stability, and sometimes electrical conductivity. And for the application ng ating polymer-based nanocomposite, pwede nga i-include po natin dyan yung packaging kasi nga po due to improved barrier properties. Pwede din gamitin si polymer-based nanocomposite for automotive parts, electronics, and biomedical devices because of its versatility, lightweight nature, and tunable properties. Ngayon, kay non-polymer naman po, non-polymer-based composite, it is use other types of matrices such as metals po in metal matrix nanocomposite or MMCs, or the ceramics in ceramic matrix nanocomposites or the CMCs. Ang non-polymer-based nanocomposite po natin are matrix material like aluminum in MMCs or silicon carbide in CMCs. Make this po composite na exceptionally strong and suitable po for high temperature and high stress environments. For the application ng ating non-polymer naman, kadalasan po siya ginagamit sa aerospace, sa defense, structural components where mas nangangailangan po ng high strength, thermal resistance, and stiffness po. Next slide po.
I'm a research professor at the Department of Mechanical Engineering at the University of Texas at Austin. I've written this book to teach a class at the regular curriculum offered to seniors and graduate students. This is my second book. For the past 10 years, I've been teaching this subject, and through the interaction with students, I actually expand the subjects on this new book that I'll be using it to teach this online class. This book was actually subdivided in 3 parts. Part 1 is fundamentals, properties, and characterization of polymer nanocomposite. The purpose of this part is to introduce to students how you could create a nanocomposite, how you actually characterize it, and know the properties of this nanocomposite you'll be creating. Part 2, it will be introduced to you the different properties that you will be able to obtain from these polymer nanocomposites. For example, mechanical properties, flammability properties, thermal properties, electrical properties, flammability properties. These are different topics I will teach for part 2. And part 3, it will be talking about the challenges and the trend of this whole field, how you could see these nanocomposites is developing into the real world as examples. Since nanocomposite is an emerging technology, a lot of different folks coming from different disciplines would like to learn about the new development. Our job is to introduce you what is the state of art of these nanocomposites, and like I said, in part 2, you can see what kind of properties you will be able to obtain from these nanocomposites you'll be developing for your work or for actually for your employer. I'm Joseph Koo. Thank you for your attention, and I would like to thank you for engaging with UT Austin faculty. Hope them horns.
Yan, bali po as if you have time po para mabasa po yung libro niya, you can search it online naman po para mas maintindihan po natin yung nanocomposite. Ngayon po, meron po tayo sa today's commercial nanocomposite, gumagamit po tayo ng 3 general nanoparticle types, the nanocarbon, the nanoclays, and the nanocrystal. Next slide po. Yan, for the first one po is the nanocarbons. Nanocarbons includes materials like CNTs or the carbon nanotubes and graphene. Nanocarbons are known for their exceptional mechanical strength, electrical conductivity, and thermal stability. They can significantly enhance the mechanical and electrical properties of the composite materials when incorporated. Next po. For the nanoclays naman po, it is a layered silicate materials that can improve the barrier properties, thermal stability, and mechanical strength of the composite. When dispersed in a polymer matrix, nanoclays can create a nanostructured network that enhances the properties like gas permeability and impact resistance. And the last one po is the nanocrystal. Next po. Or the articulate nanocrystals. It is a nanoparticles that consist of crystalline materials, often metals or metal oxides. They can improve the mechanical properties and thermal stability of the composite. Depending on the type of the nanocrystal used, they can also enhance specific properties like electrical conductivity or catalytic activity. Next slide po. Ngayon po, bago tayo mag-proceed sa application po ni nanocomposite, ano po ba yung unique kay polymer nanocomposite? Doon sa nabanggit po natin na tatlo. It increases in electrical breakdown strength of polymers po, and its melting temperature, color, magnetization, and charge capacity is mas marami. And its interacting zone is increasing such that we can get our expected property. Ngayon, for the application naman po ng ating nanocomposite, pwede po natin siya gamitin sa electrocatalyst in batteries for energy saving, lightweight materials for less fuel consumption, or pwede rin sa artificial joints, economically beneficial, and carbon nanotube, most widely speaking nanomaterial, which can be made as nanocomposite fibers. Next po. Pwede rin gamitin for abrasion and wear application. For marine application, pwede rin po for food packaging, fuel tanks, paggawa ng films, pwede rin gamitin po for environmental protection, flammability reaction, and erosion and corrosion application. Next slide po. Yan, dito naman po sa video na to is papakita kung paano ang naging application po ng nanocomposite for building constructions and civil infrastructure.
The NanoLeap project is developing a coordinated network of specialized pilot lines for the production of nanocomposite-based products for different civil infrastructure and building applications. The goal of this network is to support the research activities of European SMEs in the construction sector in nanocomposite products, enabling the progress of the product to next steps of technology deployment in order to facilitate their further adoption by the entire construction chain. For the creation of the network, 10 European pilot plants dealing with the most promising applications of polymeric nanocomposites in the construction and engineering sector have been selected. The project includes an open call for tenders to grant SMEs free of charge access to the pilot plants and consulting services of the NanoLeap network to develop or test their innovative technologies. The deadline of this open call for tenders is the 31st of December. NanoLeap, bridging innovation to market implementation.
Yan, bali po, to sum up lang po, para mas maintindihan po natin ang nanocomposite, pwede po natin siyang i-compare sa, halimbawa po yung ants po is nagke-carry po ng load. Isipin po natin yung nanocomposite, like an ant colony po, nag-work po sila together. And yung each nanoparticle po natin is a tiny, powerful member. While yung ating single ant can't move much po, together, nililip nilang object far beyond their size. So similarly po, si nanoparticles dispersed in a matrix collectively improve the strength, toughness, and functionality of the material far beyond what the base matrix can achieve alone po. So that brings us to the end of our report po. Thank you po for your attention and have a good day po.
Okay, so thank you po sa group ko ng composite. Ready na din po ba yung group, yung sinunod na po na group? Para dire-diretso na po yung presentation, and then after that po is ako na po yung mag-discuss. Ready na po ba ang biomaterials or nanomaterials po? Yun na lang kasi yung natitira natin, ano po. Yes po.
O baka hindi kayo nag-testing dun sa 40 na
Good morning, ma'am. Good morning, everyone. So today with my
Good morning.
group mates, we're gonna discuss about biomaterials. Next slide, please. So what is biomaterials? Biomaterials is a material that is intended to interface with the biological system to treat, evaluate, and treat, enhance, and replace any organ, tissue, or function of the body. They are implemented to the human body as a replacement of damaged or diseased body parts. This material should not produce toxic substance and should be compatible with the body tissue. The materials such as metals, polymers, ceramics, composites, and semiconductors can be used as biomaterials. Next slide. And here is a short video about what is biomaterials.
Until humans evolved to replace damaged or diseased tissues in their bodies like a salamander, the development of new biomedical materials will be crucial for the well-being of an increasingly aging population. Biomedical materials science is the study of how artificial materials are created for medical application in the human body, for example contact lenses, pacemakers, dental implants, and artificial joints. Millions of patients' lives are transformed every year through the use of biomaterials, giving them better vision, new heart valves, stronger teeth, improved mobility, and much more. Without biomaterials, dentists and surgeons would be unable to perform medical procedures in the way that we're used to. The Biomedical Materials Science degree course at the University of Birmingham combines biomedical science and materials science. Both subject areas are covered equally, allowing students to develop their knowledge and understanding of artificial materials and how they interact with tissues in the body. Graduates of biomedical materials science have successfully progressed in many different careers, including as a medical device specialist, senior scientist, materials engineer, and science teacher at organizations such as Pfizer, Ministry of Defense, and the NHS. Other graduates have continued their studies to master's or PhD level, with some training for clinical professions such as dentistry or medicine. If you want to study a degree program and contribute to improving the quality of life for millions of people, visit our website to find out more.
So biometallics. So biometallics is neck biometallics bio metallics biomaterials. So metals are widely used as a material for biomedical implants. There are many devices and surgical tools that are made of metal. Some of the examples of the application of the biomaterial can be like for intense metal can be used for reconstruction of the bone damage such as artificial hip, shoulder, knee, and elbow joints. Metals can also be used for fracture fixation such as plates, screws, pins, nails, and rod. It can be also used as an oral and maxillofacial reconstruction such as dental implants and many plates. It can also be used as cardiovascular intervention such as stents, pacemaker, and heart valves. Next slide, please. Metals that are used as a biomaterial should exhibit the following properties. Metal should have a high resistance to corrosion. Metal should be compatible to the body tissue. Metal should have high resistance to wear. Metals should have outstanding mechanical properties. Next slide, please. So most of the metallic material that are used as a biomaterials have a stable surface oxide layer that improves their resistance to corrosion. The material should satisfy the needed mechanical properties for their application. For example, when a metal utilize the augment a bone, the modulus of elasticity of the metal should be preferably equivalent to that of the bone. It can cause the loss of bone quality if the modulus of elasticity of the metal is greater than the bone of the bone. The bone will be remodeled to adjust to the lower load. Next slide, please. So,
here is the list of the metallic biomaterials and their properties and application. For example, titanium and its alloys, pure titanium, and the properties that has a lightweight, excellent resistant corrosion and enhanced biocompatibility. An application, it's like a pacemaker case, housing for ventricircular assist device, total joint replacement, and maxillofacial and carnofacial and dental implants. Next slide. Also, a stainless steel, because the properties of it that has low recoil and good radial strengths, good for expandability and formability, sufficient flexibility and authentic stainless steel, high temperature strengths, excellent cryogenic properties, high oxidation resistance, and application of its like a surgical and dental instrument, medical guide pins, handles for instruments, medical implants and devices. Next slide. Also, the list of the metallics of biomaterials is the cobalt chromium alloy, and the properties of it is it possesses a superior mechanical properties such as high corrosion resistance, high wear resistance, and high fatigue resistance. Well demonstrated the biocompatibility and blood compatibility of these alloys. The yield and tensile strengths of ASTM F799 alloys are 2 times as high as those for cast ASTM F75 alloy. It has excellent strength and high ductility and corrosion resistance, and devices, and more. An application of it is next slide. And Nentinol. At low temperature, it is plastically deformed, but if exposed at high temperature, it returns back to its original pre-deformed shape. An application of it is orthodontic wires, blood clot filters, self-expanding vascular stents, and medical staples. Next slide. And then tantalum. The properties of its biocompatibility, excellent resistance to corrosion. An application of it is dental implants, cerebral covering for corneal defects, coronary stents, vascular clips, and fracture fixation. Next slide. And lastly, magnesium and its alloy. The properties of it is lightweight and biodegradability. The application of it is orthopedics application, making biodegradable coronary stents. Next slide.
And now, let's proceed in talking about polymers. A polymer is any of a class of natural or synthetic substance composed of very large molecules, called macromolecules, which are multiples of simpler chemical units called monomers. Polymers make up many of the materials in living organisms and are the basis of minerals and man-made materials. With that, we can conclude that we are made of polymers, and so are trees, telephones, and toys. A polymer is a long chain of identical molecules or monomers with a range of useful properties like toughness or stretchiness. And it turns out we just can't live without them. Polymers occurs both naturally, such as DNA is a polymer, and synthetically like plastic, telepathy, and styrofoam proved how polymers have changed our world. And next slide. By proceeding in the discussion of polymer as biomaterials, let's all watch
Polymers as biomaterials. First, let's start with a case study. This is Steve. Steve is 64 years old, and on the 22nd of December 2019, he was rushed to the hospital after showing symptoms of severe chest pain, sweating, coughing, and dizziness. At the hospital, Steve was told he had suffered a heart attack caused by a buildup of cholesterol in his coronary arteries. After looking over his vials, doctors realized the best course of treatment was to insert a stent made with polymers to open his arteries. But what exactly are polymers? Polymers are large molecules made by linking together smaller monomer units. These can be linked to form dimer, trimer, and larger polymer molecules. Polymers can be divided into two groups, natural and synthetic. Natural polymers can be seen within biology. For instance, nucleotides, which are linked together to form DNA, or glucose, which can be linked to form cellulose in plant cell walls. They can also be synthetic, which are made in the lab. These include Kevlar, which is used in bulletproof vests, and polyethylene, which is commonly used as plastic wrapping. A main use for synthetic polymers is as biomaterials. These are implanted as medical devices which replace an organ or bodily function. So how did polymers help Steve? Steve
Now, the following table shows the list of common polymeric biomaterials, properties, and its application. The first one is the polyethylene. The most used polymer for total joint prosthesis is the ultra-high molecular weight, which is the polyethylene. It is chemically identical to the material used for plastic bags. Same with the bone cement, which is used with bone surgery, and plexiglass, which is used for window panes. As a property of it defined as ductile and also superior wear properties compared to other polymers, proving that it is tough. In terms of application, it is used extensively in orthopedic total joints implants such as bearing, materials in total hip, shoulder, and knee prosthesis. Next slide. The next polymeric materials is the polymethyl methacrylate or PMMA. As you can see, it has a great mechanical properties and low toxicity. As per according to the study of Lloyd et al. 2001, due to its excellent bio and hemo compatibility and ease of manipulation, the PMMA is used in many medical devices including blood pumps and dialysers. Its optical properties make it candidate materials for implantable ocular lenses and hard contact lenses, as it is used for bone cements, stabilize total joints prosthesis, and is also used to eliminate scars, wrinkles on the skin tissue permanently, and also used for dental implants such as substitute for missing roots. Next slide. The third common polymeric biomaterials was the polylactic acid or PLA and polyglycolic acid or PGA. The properties of both of these are known as biodegradable. According to the majority of recent studies, the PGA utilizes a filler materials integrated into other degradable polymers. PGA is commonly incorporated into scaffold for various tissues engineering applications such as bone, tendon, cartilage, tooth, and spinal regeneration. In short, in the process of medical application, in the orthopedics such as fixation, devices for bones and soft tissues as mentioned earlier, and dental applications. Next slide. The next one is the polycaprolactone or PCl. From the class of synthetic biopolymers, the polycaprolactone or PCl is an integral polymer with a hydrophobic liner and semi-crystalline nature exhibiting wide application in tissue engineering as well as drug delivery. Next slide. The next one is a polyhydrides. The main application of this is in medical devices and pharmaceuticals. In vivo, it is degraded into non-toxic diacid monomers that can be metabolized and eliminated from the body. Since their degradation produces a safe, it is considered to be biocompatible. Next slide. The next one is the polyurethanes. It is the most commonly used materials in the production of blood contacting devices such as heart valves or artificial veins and arteries. They comprise a large family of materials with common characteristic of presence and urethane linkage along large molecules chains. Next slide. And then the silicones. Silicone is a synthetic polymer widely used in the biomedical industry as implantable devices since 1940, owing to its excellent mechanical properties in biocompatibility. Silicone biomaterials are renowned for their biocompatibility due to its inert nature and hydrophobic surface. A timeline illustration shows that critical development periods of using silicone in varied biomedical application as it is used for caterers and for processes of replacement of carpal bones, toes, finger joints, and is widely used in breast reconstruction and augmentations and used for jaw and chin augmentation and nasal supports. Next slide. Then the hydrogels. Hydrogels are used for numerous biomedical applications such as tissues engineering, wound dressing, lubricants, contact lenses, and advanced drug delivery system. Most of them are based on synthetic or natural polymers, forming a three-dimensional network that contains aqueous media. It provides comfort to the user and have a better oxygen permeability compared to the hard lenses made from PMMA. Next. Lastly is the nanopolymers. Nano, which is small, meaning to say it can deliver the payload of a drug in a very efficient manner, leading to a high efficacy as it used as drug delivery vehicles, especially in the area of cancer therapy. Next slide. With that, we can conclude that polymeric materials can be used to enhance the stability, increase the target-specific delivery of drugs and genes, optimize the pharmacokinetics and biodistribution, and reduce the side effects and improve the efficacy of the system. Some of the polymers used for implant is biodegradable in the body. This is one of the advantages of using polymers as biomaterials. But know that the polymer is not stiff as metal or ceramic, so these materials cannot be used or not advisable to use if the implant is requiring to carry large loads.
So let's proceed to ceramics. Bioceramics are used in a variety of medical devices, from orthopedic implants like hip and knee, prostheses, to dental crowns, and even innovative tissue regeneration technologies. The remarkable properties make them ideal for use in the human body. Bioceramics must meet several tight requirements, such as being non-toxic, non-carcinogenic, and biocompatible. They should also promote tissue regeneration and integration where necessary. So let's take a closer look at some most commonly used bioceramics and their application. Next slide, please. First, we have alumina. It is one of the most widely used bioceramics, known for its excellent wear resistance, biocompatibility, and medical strength. Alumina is commonly used in orthopedic implants such as hip and knee prostheses, as well as in dental restoration like crowns. So here's a video of explaining alumina.
Aluminum oxide ceramic tubes, also known as aluminous ceramic tubes, are widely recognized for their exceptional properties and versatile applications across various industries. Aluminum oxide ceramic tubes excel as insulation components in high-temperature environments, such as furnaces and kilns. Their excellent thermal insulation properties allow for precise temperature control, minimizing heat loss and improving energy efficiency in industrial processes. With superior electrical insulation capabilities, aluminous ceramic tubes are widely used as insulators and sleeves in electrical systems. They provide reliable insulation and protection against electrical currents, ensuring safe operation in various applications, including power distribution, electronics, and high-voltage equipment. Aluminum oxide ceramic tubes exhibit exceptional chemical resistance, making them ideal for corrosive chemical processing. They can withstand exposure to aggressive acids, alkalis, and other corrosive substances without deteriorating or compromising performance. These tubes find applications in chemical plants, laboratories, and the pharmaceutical industry. Aluminous ceramic usage equipment, deteriorating or compromising performance.
So let's proceed to next common application of ceramics. Next slide, please. We have carbon-based bioceramics. This material stands out for its impressive strength, durability, and resistant to wear, and thrombosis. Carbon bioceramics are used in small joint implants and as coatings for other implants, offering excellent durability in the body. Here's a video explaining the application of carbon biomaterial.
Carbon biomaterials in ceramics. In this topic, we will be able to tackle the properties, applications, and challenges facing this type of biomaterials. Carbon biomaterials in ceramics enhance durability and wear resistance with exceptional hardness and toughness. They offer a high strength to weight ratio, making them ideal for aerospace and automotive applications. These materials maintain structural integrity under substantial forces due to their high modulus of elasticity. Carbon biomaterials also excel in thermal conductivity, crucial for efficient heat transfer in industrial and high temperature settings. Their high thermal conductivity enhances heat dissipation, preventing overheating in electronics and other applications. Lastly, their exceptional thermal stability ensures reliable performance even under extreme temperatures, making them suitable for demanding environments. They also boast high electrical conductivity for efficient electrical transfers and are corrosion resistant, making them durable in harsh conditions. Biocompatible, they are suitable for medical applications. These properties make carbon biomaterials in ceramics versatile for enhancing performance and reliability across diverse applications. In bone grafts, carbon biomaterial enhanced ceramics can fill bone defects or gaps caused by trauma, disease, or surgical procedures. They provide a scaffold for new bone growth and help in restoring skeletal structure and function. In implants, these materials create prosthetic components that replace damaged or missing bone segments. Their ability to integrate seamlessly with natural bone enhances patient mobility and quality of life. Carbon nanotubes, or CNTs, are cylindrical tubular nanostructures formed of carbon with remarkable electrical, thermal, and mechanical properties. The substance is used to increase performance in a variety of industrial items. CNTs have been extensively studied and developed as biomaterials with high function, performance, and durability in orthopedic applications. However, because CNTs are similar in size and form to asbestos, their applications as biomaterials should be cautiously approached. Here in image A, we can see an artificial heart valve, and carbon is used as a material as it is inert and biocompatible. While in image B, we can see carbon fiber being used for prostheses.
Here are some advantages. Biocompatibility. Carbon biomaterial enhanced ceramics are biocompatible, meaning they are well tolerated by the body and do not elicit adverse immune responses. This is crucial for bone grafts and implants to integrate effectively with surrounding tissues. Mechanical properties. They possess mechanical properties that can be tailored to mimic natural bones, such as high strength and elasticity. This helps in providing structural support and stability during the healing process. Osteoconductivity. Carbon biomaterial enhanced ceramics promote bone growth and regeneration by serving as a scaffold that encourages the formation of new bone tissue. This osteoconductive property is essential for successfully integrating implants and grafts with the existing bone structure. Durability. These ceramics are durable and resistant to degradation over time, ensuring long-term stability and functionality of implants and grafts. Lastly, versatility. Carbon biomaterials can be engineered to have specific surface properties that enhance cell adhesion and proliferation, further supporting tissue regeneration and integration. Conclusion. Carbon biomaterial enhanced ceramics offer a game-changing innovation in various industries due to their excellent characteristics and wide application range. These materials are superior in mechanical strength, thermal conductivity, and electrical performance, making them indispensable in the aerospace, automotive, and electronic industries. Furthermore, their biocompatibility and corrosion resistance make them suitable for medical applications, particularly bone transplants and dental implants. Carbon biomaterial enhances ceramics' capacity to support bone regeneration while integrating smoothly with natural tissue highlights its critical significance in improving medical treatments and patient outcomes. As research and development efforts rise, these adaptable materials promise future advances in the industrial and healthcare sectors, propelling progress towards more efficient, durable, and sustainable technology.
Next slide, please. Next, we have the calcium phosphates, including hydroxyapatite and tricalcium phosphate. These materials are found naturally in the human body and highly favored for bone generation. They serve as templates for cell growth and healing, making them ideal for bone-related medical devices. Despite being brittle, their high compressive strength and ability to slow degradation in the body make them invaluable for tissue regeneration. Here's the video for about calcium phosphates.
Imagine a world where every dental implant not only integrates seamlessly, but also revitalizes the very bone it touches. This is the power of bioactive calcium phosphate surface, a true game changer in dental technology. From the moment an implant is placed, our bioactive surface begins its transformative journey. It strengthens and fortifies the bone, calling osteoblasts into action to lay down a robust foundation of calcium phosphate crystals. The result? A bond so strong it becomes one with the natural bone. As time goes on, the magic continues. The surface's gradual resorption releases vital minerals that fuel the ongoing cycle of bone regeneration. Osteoclasts and osteoblasts dance in perfect harmony, maintaining the health and integrity of the bone matrix, ensuring that your implant remains steadfast for years to come. Why settle for ordinary when you can achieve extraordinary? With creating a dynamic, living bond that adapts and active calcium phosphate alongside you. It's more than just a surface. It's the future of dental implants, where innovation meets nature to redefine what's possible. Thank you for watching.
Next slide, please. Then we have the calcium sulfate. This is commonly known as plaster of Paris. It is another bioceramic used for its rapid resorption and biocompatibility. This material is often used in bone regeneration procedure where quick resorption is needed to facilitate new bone growth. Here's a video explaining plaster of Paris.
Hello and welcome to the Health Fairy Undiluted. Ever wondered how plaster of Paris is made or how it aids in bone healing? Well, the process is quite fascinating. Plaster of Paris, a quick-setting gypsum plaster, is a substance that has found its way into a multitude of applications, especially in the medical field. The name plaster of Paris might paint the image of the Eiffel Tower or the Louvre in your mind, but it's actually derived from the large deposits of gypsum found around Paris. It's not just about the city of love, but also the city of plaster. This versatile material is used to create artistic sculptures, moldings, and even in dentistry. But what has truly marked its significance is its role in the medical field, where it's used to create sturdy and reliable casts for broken bones. Intrigued? Well, hold on to that curiosity as we're about to delve deeper into the process. Creating plaster of Paris involves a series of steps that transform the raw material into the product we all know. It all begins with the extraction of a naturally occurring mineral known as gypsum rock. This rock, when subjected to heat at a specific temperature, undergoes a process called calcination. During this heating process, the gypsum rock loses around 3/4 of its water content and converts into a dry white powder. This is our plaster of Paris in its raw form. But here's the trick. When water is added to this dry powder, a remarkable transformation occurs. The plaster rehydrates, reverting back to its original form, gypsum. This reaction is fascinating because it's exothermic, meaning it releases heat. This is why plaster of Paris feels warm when it's setting, so that's how plaster of Paris is made, but how does it aid in bone healing? It's quite remarkable how plaster of Paris helps in the process of bone healing. This humble material plays a pivotal role in mending what's broken. When a bone fractures, it needs a stable and supportive environment to heal, and plaster of Paris casts provide just that. You see, the plaster hardens quickly, effectively immobilizing the bone. This quick action ensures that the bone remains in the correct position, allowing it to mend without further complications. But the magic of plaster of Paris doesn't stop there. It's not just about the hard shell it forms. This material also breathes. It allows air to circulate, which is absolutely vital for the healing tissues underneath. In this fascinating world of medicine, where high-tech equipment and complex procedures often steal the spotlight, sometimes it's the simplest things that make the biggest difference. It's amazing to think that a simple substance like plaster of Paris can play such a crucial role in healing and saving lives. Thank you for watching. If you like this video, comment, like, and share, and don't forget to subscribe to the Health Fairy channel for more information on.
Next, we have the bioactive glass. Bioactive glass is a fascinating material that actually bonds with human tissue, used primarily in dentistry. It's biocompatible and can stimulate bone formation and tissue healing. Its ability is to form strong bond with bone tissue makes it ideal for dental restoration and bone repair. Here's a video explaining bioactive glass.
Hello, my name is Nadim Kalailat. I'm going to talk today about bioactive glass. I'm going to talk about its importance, its composition, how it is prepared, some of its properties, and its applications in dentistry. Bioactive glass was developed as a result of the research to find a restorative material that combines the mechanical abilities of ceramics and amalgam and the bioactive and aesthetic properties of cements and composites. Its main purpose of use is its ability to deposit hydroxyapatite while preserving high bonding strengths without rejection from the human body. This is the commercial form of bioactive glass. It's called BioGlass 45S5. There are 3 generations of bioactive glass that were used: an original generation, Class A and Class B. The original generation contains 45% silicon oxide, 24.5% sodium oxide, 24.5% calcium oxide, and 6% phosphorus oxide. The other generations include these constituents. Bioactive glass may also contain biocompatible additives like fluoroapatite, wollastonite, which is a silica-based glass, and tricalcium phosphate. Sodium was thought to be an essential component, but sodium-free bioactive glasses have shown same levels of bioactivity. Also, apatite formation is highly affected by the amount of magnesium oxide, spinel, and phosphate. Other ions may be added like fluoride, copper, and zinc to enhance the bioactive and antimicrobial effects. Initially, the techniques of manufacturing bioactive glass consisted of heat treatments, then quenching to freeze atomic structure. But this technique proved to be flawed and ineffective, since high sintering temperatures reduce the bioactivity and ion dissolution. To add on, heat treatments cause the formation of crystalline phases in the glass that severely decrease the elastic modulus and strength, leading to easy fracture and failure. A newer technique was developed, and it's based around the sol gel foaming process by treating the contents of bioactive glass to various processes like hydrolysis and condensation reactions, followed by low temperature treatments. This formed sol gel, when exposed to fluids in the oral environment like saliva, undergoes ion dissolution, which is essential for hydroxyapatite deposition. However, the interesting part about this is finding the right size for the particles, because small particles give low mechanical properties and good antimicrobial capabilities, but large particles prompt good mechanical properties but decrease the antimicrobial capabilities of the glass. Bioactive glass was first discovered or developed in 1985 by Larry H. Deach, but it's under constant evolution and development, as we will see later on. That's why I will talk about it today. Bioactive gas has 2 main properties: bioactivity and its antimicrobial properties. Once in contact with body fluids like saliva, bioactive glasses immediately undergo ionic dissolution and glass degradation via the exchange of hydrogen ions in the solution and sodium and calcium ions from the glass network. The ion exchange results in the formation of silynyl groups, silicon, oxygen, and hydrogen, due to the hydrolysis of the silica groups. An increased alkaline environment then develops because of the increase in hydroxide concentration. The silica network is further degraded as the pH rises, forming orthosilicic acid and silicon hydroxide on the surface in the form of a negatively charged gel. This gel layer functions as a matrix for hydroxyapatite deposition. Bioactive glass has a very important role in combating periprostatic joint disease since its bioactive properties prevent inflammation and infection of vital tissues. Bioactive glasses also have shown to possess broad spectrum antimicrobial properties with no observed resistance to date. Once embedded in the body, bioactive glasses increase the pH and osmolarity locally as part of their hydroxyapatite deposition reactions. This creates an environment unfriendly for bacterial growth. Bioactive glasses have many applications in dentistry, some of which are their use in dental adhesives. Since some versions of bioactive glass can deposit fluoroapatite, they can be used as dental adhesives in orthodontic treatments to solve the issue of white spot lesions. But care should be taken in the addition of fluoride, since its amount affects mechanical properties. Also, bioactive glasses are used in adhesives since the deposited hydroxyapatite, when in contact with dentin, reacts with the tissue inside the dentinal tubules, resulting in dentinal adhesion and therefore providing a stronger bond. Another use for bioactive glass is in restorative dentistry. What we face today, or the main issue with mainstream restorative materials today, is their polymerization shrinkage upon application. This decreases marginal integrity that accelerates the formation of secondary caries. However, bioactive properties of bioactive glass and its ability to remineralize enamel and deposit apatite prove to be essential for achieving the perfect restorative material. That's why other materials are added to the bioactive glass compound. For example, fluoride impregnated bioactive glass was found not only to increase remineralization, but also reduce enzymatic degradation of the dentine collagen network. Also, the increased concentration of silver bioactive glass resin composite increased the number of dead bacteria in biofilm when compared to other samples. So, we can say that silver enhances the antimicrobial properties of bioactive glass. Also, bioactive glass was incorporated into GIC in an attempt to produce a cement with the mechanical characteristics of a resin composite and the antimicrobial properties of GIC. It was proved later that bioactive glass enforced GIC has a higher flexural strength than regular GIC, but this experiment was of little success, since it was found that the other mechanical properties were actually compromised. Therefore, this application of bioactive glass is only advised in low-stress situations. Bioactive glass can also be used in pulp capping and root canal treatments. because an in vitro study showed that the ions released by bioactive glass particles did not inhibit the growth of human dental pulp cells, but it showed that when bioactive glass was used for direct pulp capping, a dense dentine bridge was formed. Bioactive glass is also used in getaperca since it enhances its bonding to dentine walls without an adhesive. It also provides a tight seal, increases the pH, and provides antimicrobial action. The BioGeta, it's a commercial form of bioactive glass used in getaperca, and it's as new as 2018. That's why I'm talking about bioactive glass, because it's under constant development. The final use for bioactive glass is in dental implants. Since bioactive glasses might help implants bond activity to bone, they are used in dental implants. Also, they provide antimicrobial protection and a reduction in total treatment time. Also, they're less invasive than the periodontia. In conclusion, the chemistry of bioactive glass mimics the natural hard tissue's composition and has a bioactive role in the regeneration. The FDA recently has approved bioactive glass in its commercial form BioGlass 45S5 for clinical applications due to the desired antimicrobial properties. This has caused an increase in the use of bioactive glasses in various aspects of dentistry, including dental restorative materials, pulp capping, and RCT treatments, and even in periodontics. I can say that it seems bioactive the miracle restorative dentistry has been praying for. This is my reference. Thank you.
Lastly, we have the nanoceramics. With a much smaller particle size, these materials offer a larger surface area, increased porosity, and enhanced surface reactivity. Nanoceramics are being used in various medical applications, including implantology, drug delivery, and cancer therapy, and even gene therapy. There's a video explaining nanoceramics.
Assalamualaikum. Our today's topic is, rather question is ceramics and nanoceramics materials. The question is taken from General Science Ability paper 2023 of CSS. The question is comprises of three parts. In the first part, it asked, define ceramics and nanoceramics materials, and then why do nanoceramics materials show better properties, and then ask about their applications. So we are moving toward the definition of ceramic materials. Ceramic material defined as ceramic is a Greek word meaning pottery, which you call in Urdu bartan. So ceramics are a class of hard but brittle materials. Now, what kind of materials are brittle are? When a brittle material fall on ground, it tore into pieces like this. This is a brittle material, but this one is a non-brittle material. A non-brittle material only break or fracture from its weakest part, but a brittle material tore into many pieces. So a ceramic is a class of hard but brittle materials produced from inorganic compound, usually clay, shaping the clay into a particular shape and then firing them at high temperature. Like first we shape this clay and then fire at high temperature to give it this shape. Ceramics are known for their excellent heat and electrical insulation. Like they are insulator, they don't conduct heat and electricity. And they're also resistant towards chemical and physical wear and tear. Their example are tiles and plates. These are all their examples. So this is of ceramic materials. Ceramic materials application are in the field of tableware or kitchenware, like utensils that we used in on our dining table or in our kitchen. And then its application are in tiles and flooring and dental implants, like tooth replacement. So in tableware or kitchenware, ceramics are commonly used in the production of plates, bowls, cups, etc. And in tiles and flooring, ceramic tiles are widely used for flooring in homes and commercial spaces. Dental implants, bioceramics like zirconia are utilized in the production of teeth implants. Like we replace our damaged teeth with the teeth that are made with ceramics, and it just look and work like a natural teeth. So these were the application of ceramics. Now we are moving toward nanoceramics materials or nanoceramics. Nanoceramics are like super special ceramics. They are ceramics, but they are the best, are the super, are the tiniest form of ceramics. Imagine making ceramics like you are making normal ceramics, but like pots or tiles, but really small, like too small to see with your naked eyes. You are making ceramics, but in its smallest, in its tiniest form. And these super tiny ceramics are super strong. Now, due to their tiniest form, their smallest form, they are super strong. They work well in tiny electrical gadgets and even help in medicines. So if we want to define ceramics in better words, we can say that nanoceramics are advanced materials that combine the properties of ceramics with nanotechnology. They are created by manipulating materials at nanoscale and at its smallest scale, which involves structures and particles that are incredibly small, usually less than 100 nanometers. So these were the definition or a brief description about nanoceramics. Now, why do nanoceramics show better properties than traditional ceramics? Nanoceramics outperform traditional ceramics, like they show better performance than traditional ceramics due to their increased surface area. Due to their increased surface area, they show better performance. It is due to this property that they show they boost reactivity and allow for tailored structure. Like we can convert them, we can shape them in any structure we desire, we want. This lead to improved mechanical strength. This property enhance their mechanical strength and thermal and electrical conductivity. Now they can conduct electricity and heat, and also they are more strong than traditional ceramics. Moreover, reduce grain boundaries. Their boundaries are now reduced. Due to this performance, they are crucial. They are crucial in cutting tools and electronics. Now they can be safely cut into our desired shapes, and they can be used in electronics. In biomedical or in the field of medical, they can be used in implants. Like you can replace your limb or a fractured joint or any other part of the body or teeth with the ceramics prepared teeth, limb, or a joint, and also used in drug delivery. So moving toward the application of nanoceramics are used in biomedical implants, they're used in electronics, they're used in catalysts. When a person lost joint or limb, ceramics made joints or limb is implanted, and they work just like a normal limb or joint. In electronics, ceramics are used in production of nanoscale capacitors and semiconductors. And in catalysts, nanoceramics serve as effective catalysts in chemical reactions due to their increased surface area and reactivity. So it was all about ceramics and nanoceramics, their applications.
Those are the common use bioceramics and their applications. Now we will proceed to natural biomaterials.
Next is we have natural biomaterials. Like synthetic materials, natural materials can also be used as biomaterials. Natural biomaterials are used for different medical applications due to their biocompatibility and ability to support cellular functions. Natural biomaterials has few requirements. This material must be non-toxic, non-allergic, non-inflammatory, having excellent mechanical properties, capable of inducing cell attachment and differentiation if needed, and it has to be low cost. Now, here we have the commonly used natural biomaterials and their properties and applications. First is we have collagen, known for its resorbable, non-toxic nature and low immune response. It is used for tissue regeneration and wound healing. Second is elastin. With high durability and flexibility, elastin is used for vascular stents and various tissue repairs. Next is silk. Biocompatible with slow degradation and strong mechanical properties, silk is often used for medical sutures. For minimizing foreign body reactions, chitosan is used. Next is we have chitosan in wound dressings and cartilage repair. Next is cellulose. Known for its strength, it is used in burn therapy as artificial skin and as tablet binder in pharmaceuticals. Next is alginate. Biodegradable and muco-adhesive. It is used in wound dressings and dental prosthetics. Next is hyaluronan. Known for its hydrating properties, it's used in tissue regeneration, wound healing, and as part of extracellular matrices. Next is chondroitin sulfate. Used for cell adhesion and growth, it's applied in tissue engineering and as surgical aid. Then lastly is coral. Biocompatible with bone-like mechanical properties, coral is utilized in bone defects filling and reconstructive surgeries. Next is we have example of biomaterials.
So for the examples of our biomaterials, these are the applications that we humans use in our society. So for our first example is an intraocular lenses. It is made of PMM, silicone, elastomer, and other materials. After lens is inserted, good vision is restored immediately. So as we all know, this is commonly used in cataract surgery. So ito po yung process niya. Then ito po ay isang artificial lens for the eye and it replaces the eye's natural lens that is removed during cataract surgery. So na nangyayari po dito is nagkakaroon po ulit tayo ng sa mga nag-undergo po ng cataract surgery. Nagkakaroon na po ulit sila ng good vision. For next po is next slide po. So next is a heart valve. It is made from carbons, elastomers, metals, fabrics, and natural valves. It is attached by polyester mesh. The tissue growth facilitated by polar oxygen-containing groups. After the valve implanted, cardiac function is restored to near normal. The most widely used is the bilaflet tilting disc heart valve. So for our heart valve, it is commonly used especially during any surgery that includes heart problems. So if mahina na po yung heart natin, there is a biomaterial that could be used para po makapag-function po ulit ng yung heart natin ng normal. Then next slide po. Next example would be dental implants. Titanium are the common materials used as a replacement for the root portion of the missing natural tooth. It is placed in the bone of the lower and upper jaw. Most dental implants are pure titanium screw-shaped cylinders that act as roots for crowns and bridges or as supports for dentures. It should be bio-inert. There is no reaction in tissue and no rejection or allergic reactions. So in this case po, dental implants, ito po yung ginagamit natin for our some dental surgery or if gusto po natin magkaroon ng permanent na tooth for replacement po. And the material used should be, hindi po dapat siya magkakaroon ng allergic reaction or anything harmful to our gums or in the nerves. Nagpagagamitan po natin ng ating dental implants. So next po is a vascular grafts. Vascular graft should be good structure, retention, flexible, high fatigue, resistance, adequate burst strength, good handling properties, and biostable. It is designed with open porous structure. It is made of polyethylene terephthalate, PET, or Dacron. So next slide po. Hip replacements, it is made of corrosion-resistant, high-strength metal alloys or very high molecular weight polymers. So in this case po, ginagamit po ito as a hip replacement po for some surgeries po.
Up next po, we have kidney implants. Artificial kidney is a device that works like a normal kidney. The unit is divided into several parts where it enters the blood and is filtered after absorbing the nutrients and discarding waste substances. Now, a fun fact po about kidney implants is that an implanted kidney only naglalast po siya about 12 years. So after a recipient of a kidney transplant, it is partially keep on being replaced after 12 years due to the fact that it is powered through maintenance. Ganun po. And up next, we have artificial hearts. This is also a mechanical device used in order to bridge the time for heart transplantation or to replace permanently the heart if transplantation is impossible. This heart consists of formed using synthetic material and has power supplies. Now, as said po, if a recipient or a patient is requiring heart transplant and there is no available donor, doctors would use artificial hearts to fill in what's missing of the patient. Now, just like the kidney transplants, artificial hearts also needs to be replaced every after 4 years if it's the only option because it is battery operated. Next example po would be the pacemaker. This is a device that uses electrical impulses contacting the heart muscles. It is of a pager-sized housing device that contains a battery and the electronics circuit that runs the device, along with one or two long thin electrical wires that travel from the pacemaker. Now, looking po at the image, we see that the pacemaker is connected to the heart. Now, this is a very important device and it is one of the delicate artificial or biomaterial things out there because if a patient has a pacemaker, they are not allowed to be in contact with anything magnet used. So, for example, even a cell phone isn't allowed to be anywhere near the pacemaker's location within the body. Next po, we have the contact lenses. This is a corrective lens placed on the cornea of the eye, designed to improve vision because some people have a mismatch between the refractive power of the eye and the length of the eye, leading to a refraction error. Now, it is most common that this is probably the most used biomaterial example that we have in our world. A lot of people would rather prefer using contact lenses than wearing glasses because it's much more convenient. And fortunate for us, modernization really took advantage of this of this product that we are using to this day. And last but not least, we have bone cement. It is used to anchor artificial joints such as hip joints, shoulder, knee, and elbow joints. And that is it po for biomaterials. I hope you learned something from us and realize the importance of the examples we used in this presentation. It is important to understand that our world relies solely and relies actively on biomaterials nowadays. And fortunate that scientists are able to improve these materials for us to further progress our lives. Again po, we are Group 4 from ME 3106 and this is Biomaterials.
Okay, so thank you so much po sa group po ng biomaterials. Okay. So medyo mabilis lang po yung mga video. Ano po? Wala akong naintindihan sa video. Okay. Anyway po, ang next po natin is yung last na po na magpe-present is the nanomaterial. So ready na po ba ang nanomaterial? Not yet? Or ready na po? Hanggang anong oras nga pala yung klase natin? Hanggang when pa naman po ano po?
Yes po.
Yes po.
Okay. So, ready na po ba ang nanomaterial po? Okay. So, next week naman po ay ang atin pong time is sakop na po ng experiment. So, sa sunod na week po is ako na po ulit lahat po ang magsasalita. So, ibabalikan lang po natin yung mga other material pa po. So, i-ano po natin yung mga mahalaga pong part po ng kada material. Okay? So, asa na po ang nano? Nandito po ang group ng nano material. Hello?
Yes po, ma'am.
Okay. Ready na ba kayo for the presentation?
Yes po.
Okay po. Okay, so you may proceed with your presentation.
Good morning, everyone. Today, we're going to talk about nanomaterials, their types, properties, and applications. Next slide po. So, what exactly are nanomaterials? Next slide po. Kindly watch and listen carefully to this video to gain a better understanding of nanomaterials.
What are nanomaterials and what are they for? Nanoscience has managed to get a wide variety of specialists from very different knowledge areas, engineers, chemists, physicists and biologists, all working together. Today, we know that material on the nanometric scale has chemical and physical properties that are quite different from those of the same material on a larger scale. This has made it possible to design materials with unique applications. One of the main characteristics of nanoscale materials is that they have a high proportion of surface area in relation to their volume. They are also known for a phenomenon called quantum confinement, which comes about when the movement of electrons is highly restricted. This increases the chemical reactivity and changes the optical, electronic and magnetic properties. These materials can be built by using top-down techniques, that's to say, fragmenting larger pieces of material, or atom by atom or molecule by molecule techniques. New medicines and cosmetics, more efficient sensors and tissues will revolutionize the consumer industry, building materials and water treatment.
In addition, nanomaterials are special materials with a size scale in the range of about 1 to 100 nanometers. To put that into perspective, a nanometer is a billionth of a meter. This is way smaller than a cell in our body, even smaller than many viruses. Because of their tiny size, nanomaterials can have unique properties like increased strength, different optical or electrical behavior, or even enhance chemical reactivity. These properties make them useful in a wide range of fields, from electronics and medicine to environmental cleanup and energy. Next po. Nanomaterials come in several types, each with its own unique characteristics and uses. Number one is the carbon-based nanomaterials. As the name implies, these nanomaterials are primarily composed of carbon. They commonly appear as hollow spheres known as fullerenes or as tiny cylindrical structures called carbon nanotubes. So why are they special? Carbon-based nanomaterials are super strong yet very lightweight. This strength combined with their unique structure makes them ideal for electronics, coatings, and films that need to be durable yet light. Next po. Second is metal-based nanomaterials. These nanomaterials are made from metals like gold, silver, and even metal oxides. Some of them, like quantum dots, are tiny crystals that change color or behavior depending on their size. Because of their unique optical properties, metal-based nanomaterials are often used in imaging, sensors, and even as antibacterial agents in medical products. Next po. Next is dendrimers. These are complex branch molecules that resemble tiny trees. Each branch can be customized to do a specific job, like delivering drugs in the body. Dendrimers are especially useful in medicine because their branching structure allows them to carry multiple drugs molecules or target specific cells. And lastly, the composites. Composites are a mixture Composites are a mixtures of nanoparticles with other materials, often larger ones. By adding nanoparticles to other materials, we can create composites that are stronger, more heat resistant, or even flame retardant. For example, think of nanoclays added to a plastic. This can make the plastic more durable and less likely to melt at high temperatures. Next po. In addition to the different types of nanomaterials, we also have three main types of nanocomposites. Nanocomposites are materials that combine nanoparticles with other substances to enhance or add new properties. First is zero-dimensional nanocomposites. In zero-dimensional nanocomposites, Nanoparticles are evenly spread throughout a material called a matrix. The key feature is that these particles don't touch each other. They stay separate within the matrix. Next is one-dimensional nanocomposites. This type consists of nanostructures like nanotubes or nanorods that are arranged in a matrix. These structures provide a specific direction of strength or conductivity because of their shape. And lastly, two-dimensional nanocomposites. In two-dimensional nanocomposites, thin layers or films are stuck on top of each other within the matrix. Each layer can be made from different materials, and this layering allows the composite to have unique properties like flexibility combined with strength or enhanced conductivity. So these three types, zero-dimensional, one-dimensional, and two-dimensional, are designed based on the shape and arrangement of the nanoparticles. Each structure gives the material in different set of strengths, whether it's increased durability, direction, specific strength, or flexibility. Next po.
And now I'll discuss the properties of nanomaterials. There are four properties of nanomaterials, and the first property is optical property. Optical property of the nanomaterial is one of the most fascinating and useful aspects of nanomaterials. Nanomaterials can be used for optical detector, sensor, laser, imaging, phosphor display, photocatalysis, solar cell, electrochemistry, and biomedicine. The optical properties of nanomaterials depend on parameters such as feature size, surface characteristics, shapes, and other variables including doping and interaction with the surrounding environment or other nanostructures. Next slide, please. The second property is electrical property. Electrical properties of nanoparticles discuss about fundamentals of electrical conductivity in nanotubes and nanorods. Carbon nanotubes, photoconductivity of nanorods, electrical conductivity of nanocomposites. One interesting method which can be used to demonstrate these steps in conductance is the mechanical thinning of a nanowire and measurement of the electrical current at a constant applied voltage. The important point here is that with decreasing diameter of the wire, the number of electron wave modes contributing to the electrical conductivity is becoming increasingly smaller by well-defined quantized step. Next slide. And the next property is mechanical property. Mechanical properties of nanoparticles deals with, with bulk metallic and ceramic materials, influence of porosity, influence of grain size, superplasticity, field polymer composites, particle field polymers, polymer-based nanocomposites filled with platelets, carbon nanotube-based composites. However, two materials, neither of which is produced by pressing and sintering, have attached much greater interest as they will undoubtedly achieve industrial importance. These materials are polymers which contain nanoparticles or nanotube to improve their mechanical behaviors and severely plastic deformed metals, which exhibits astonishing properties. However, because of their larger grain size, the latter are generally not accepted as nanomaterials. And the last property is magnetic properties. Both gold and platinum are non-magnetic, but at the nano size, they are magnetic. Surface atoms are not only different to bulk atoms, but they can also be modified by interaction with other chemical species, that is, by copying the nanoparticles. This phenomenon opens the possibility to modify the physical properties of the nanoparticles by copying them with appropriate molecules. Actually, it should be possible that non-paramagnetic bulk materials exhibit paramagnetic-like behavior when prepared in nanorange.
Now, moving on po, I will discuss the selected applications of nanomaterials. So,
For the first one po, let us watch this video.
In many parts of the world, people rely on costly oil and gas lamps, candles, and inefficient torchlights to light their homes, risking daily exposure to toxic fumes and fire hazards. An affordable, safe, and pollution-free source of light, if it could be found, would help to solve this problem. A microbial fuel cell, or MFC, is a device that works by tapping the energy that microbes generate as they break down organic matter. In its simplest form, MFCs can be a container with wastewater connected to positive and negative poles hooked up to a circuit board, a bit like a battery harvesting electricity from wastewater. So all you need is dirt and a few components to supply energy. Each MFC produces a small amount of electricity. By connecting lots of them together, it's possible to obtain a current that could be used to power small devices like LED lights or charge mobile phones. Microbial fuel cells can be constructed using low-cost materials that are readily available and don't add to pollution, such as recycled plastics and electrical components. They require little maintenance, can be easily assembled, and have great potential as a source of energy for remote areas with no access to the electrical grid or other forms of renewable power. They could also be embedded within cities, in parks and green areas. MFCs can contribute to urban greening by treating wastewater, providing renewable energy, and even growing plants.
Then ito po, may isa pa po ulit video.
Did you know that catalysts are one of the most important components in chemical processes? They're used to make high-end products like food, coatings, and plastics. And to make sure that the catalyst behaves the way we'd like it to, we need to make sure we can control their properties. To make catalyst particles in a controlled way is not that trivial. And that's where my project steps in. I work on it from a colloidal point of view. So I make really well-defined nanoparticles and build a catalyst particle from that. Nanoparticles are really small particles that are 1,000,000 times smaller than a millimeter. And despite them being so small, we can exactly tune their composition, shape, and size. And this makes them ideal building blocks to build up larger structures with great functionalities. One of those functionalities could be catalysis. In my work, I focus on 2 different nanoparticles. One nanoparticle is catalytically active, while the other nanoparticle supports the catalyst. And with that approach, I am able to control the catalyst particle on multiple length scales and design a better catalyst that does not look like this conventional particle, but more like this highly ordered catalyst. This self-assembly approach allows us to make the catalyst particle with the greatest control, such that we can work towards the best possible catalyst.
So discussed from the previous 2 videos are the first 2 selected applications of nanomaterials. So first one is the fuel cells. So nanomaterials can be used as fuel cells, like the microbial fuel cell, which is a device wherein a bacteria consumes water-soluble waste such as sugar, starch, and alcohols and produces electricity plus clean water. And this technology will make it possible to generate electricity while treating domestic or industrial wastewater. So another one is the catalysis. Catalysis, or because of the nanomaterials smaller scale, they have higher surface area available. And in comparison with the natural enzymes versus the nano enzymes, so una, ano bang ginagawa muna ng catalysis? So they speed up the process ng yung mga certain processes rather than walang enzymes or nano enzymes na involved. So yun. Moving on. The next 2, the other 2 applications.
Nanotechnology is the buzz of the world today. Here are some lesser-known facts about this emerging technology. The wonder material that has wide range of applications and offers lots of benefits is none other than graphene. Let us understand graphene better for our day-to-day use. Graphene is rapidly finding its way into a wide range of applications and offers a number of benefits. For instance, it is used for developing innovative products as well as improving certain properties in currently available products. An allotrope of carbon, graphene exists as a two-dimensional, 2D, planar sheet and can be regarded as a single atomic graphite layer. Technically, graphene is a non-metal, but it is usually known as a quasi-metal because its properties are similar to that of a semiconducting metal. Graphene possesses a number of unique properties that cannot be found in other non-metallic materials. Since graphene has many unique properties, it is ideal for use in electronic applications when compared to other traditional materials. Graphene is also known to possess good mechanical, thermal, and optical properties. Graphene can be synthesized by 3 different ways. They are as follows: chemical vapor deposition, mechanical cleavage from natural graphite, chemical or plasma exfoliation from natural graphite. Graphene can be used in functional inks for electronic, anti-corrosion, and heat-resistant purposes. By combining graphene into ink formulations, the conductivity properties related to graphene influence the ink, causing it to turn conductive. The inks can subsequently be used to coat electronics. Graphene is non-toxic, environmentally friendly, cheaper, quick-drying and recyclable than other conducting inks. Graphene also possesses a high thermal stability, making it suitable for heat-resistant ink coating in electronic applications that create large amounts of heat. For more interesting facts and updates on nanotechnology, subscribe to Nano TV. Nanotechnology is the buzz of the world today. Here are some lesser-known facts about this emerging technology.
Electronics have become part of our life, but rarely do we bother to engage with the technology that is driving these modern gadgets. Here we look at the role of nano in electronics, called nanoelectronics. Nanoelectronics aims at improving the capabilities of electronic devices and displays while shrinking them and reducing their weight and power consumption. Nanoelectronics covers a diverse set of devices and materials, with the common characteristic that they are so small that physical effects alter the material's properties on a nanoscale. Interatomic interactions and quantum mechanical properties play a significant role in the workings of these devices. Nanoelectronics holds significant promise for expanding the abilities of electronics devices while reducing their size, weight, and power requirements. Display screens can be improved by cutting power requirements while lowering the weight and density of displays. Scientists are also working on a kind of nanoscale memory chip capable of holding 1 terabyte of data per inch 2 or more. The age of wearable electronics is upon us, as witnessed by the fast-growing array of smartwatches, fitness bands and other advanced, next-generation health monitoring devices such as electronic stick-on tattoos. Solar cells and supercapacitors are examples of areas where nanoelectronics is playing a major role in energy generation and storage. Distinct from nanoelectronics, where devices are scaled down to nanoscale levels, molecular electronics deals with electronic processes that occur in molecular structures such as those found in nature, from photosynthesis to signal transduction.
For more interesting facts and updates on nanotechnology, subscribe to Nano TV.
And for the last 2 applications, first we have phosphors for high definition TV. The resolution of a television or monitor depends greatly on the size of the pixel. These pixels are essentially made of material called phosphors. which glow when struck by a stream of electrons inside the cathode ray tube. The resolution improves with a reduction in the size of the pixel or the phosphors. Nanocrystalline